Okay, let's continue. So I guess I can sort of review very quickly, just recap what we almost just talked about. So I was discussing crossing property. So here is quick summary of what we could talk about. So we imagine there's some interaction. So we talk about the two-to-two scattering. And then I was telling you that I'm gonna take a convention that all the charge flew are towards the center of the vertex. And then we will assign also momentum such that everybody goes in like this. Okay? Then by momentum conservation, obviously, energy momentum conservation, this has to satisfy this, right? So clearly. Then the first point I discussed was that if there's a momentum I, such that whose zeroth component is positive, meaning energy is positive, then you can literally take as it is, meaning, so suppose energy of this is positive, this is good to be used. So this then describes incoming, meaning, by incoming here, I mean that the particle motion trajectory is along the momentum itself. I'll also show you that. And in particular, in this chart, in this assignment, it corresponds to incoming particle. Okay, so that's all I talked about. If, say, there's another guy whose zeroth component is negative, then, as I explained, then physically sensible actual momentum actually corresponds to minus of that thing rather than itself, right? Hence, this describes the outgoing, by which I mean now the particle motion. I combine the particle and motion. Beautiful. Particle motion is actually against the momentum. Okay? So then this describes outgoing anti-particle. Okay? So that's that. So with this, then I introduced for two-to-two scattering, I say that we can use Mandelstam variable. STU. So let me now repeat rewriting all the definitions. And so amplitude is a function of ST and then I said that this is a overcomplete set in a sense that this has to satisfy a constraint equation, as I showed in the last lecture. So in fact, this shows that this amplitude is a function of 2 of ST. Okay, in principle. But we can continue to use these 3 variables because they will manifest the existing structure, precisely crossing structure in this theory or in this amplitude. So that's what we said. And so then I introduced Mandelstam plane. So this is Mandelstam plane. So this S increases starting from here up, okay? And this is literally plotting this constraint equation I just showed, right? Increasing as you put it in space. And then this is T, and T increases towards that. This is U, and then it increases towards that. And then I sort of plot something, but let me actually do it. So if we have a process, so S-channel process is such that actually the S here, which is P1 plus P2 squared, plays the role of the total energy. Okay, and then T, U will be momentum transfer. We said that's S-channel process, but then as I discussed, is bounded from below like this, assuming in this discussion I will assume that everybody has the same S. Okay, so here I assume, so on this discussion I will say that the entire mass is basically the same. Okay, and I will comment on what happened if we consider different masses, but for now let me just take this to be the case. So with that I plot that this corresponds to this one. Okay, so this corresponds to S channel. Because you can saturate this 0 when this is less than or equal to 0, okay, because there's a minus sign if you have to compute T and U. And then you saturate when this becomes exactly 0, so that's T less than 0, U less than 0, and then S equal to greater than or n squared, so that's it. So that's this S channel. And then one can do the same thing. So T, when T reaches for n squared and above, this corresponds to T channel. And then this corresponds to U channel. Exactly the same. So I don't need to write the same thing. So T channel where T plays a role of total energy, U channel where U plays a role of total energy, the other two plays a role of momentum transfer. Okay? So that's that. And this particular drawing, that's big bad. Is understand cable. So then the point is the following. The point of the crossing property is that given an amplitude, okay, which will be a meromorphic function of ST, meaning it's in general function of a complex momenta and there might be singularities, okay, poles and branch cuts. And other than those singular point, this will be analytic function. So that's a meromorphic function. So same amplitude can describe a process in S channel if we take STU in a proper value. So for instance, take that function and go to the region where S is equal or greater than 4n squared, and this is equal less than 0. Okay, then that amplitude give you an amplitude for S channel process. I will discuss an example. Take the same function. Yes.
The particle not available for Zahn statistics, or
I will talk about that. Very good questions. I will talk about that almost right away. Take that function, and then now, if you go to the regime that is consistent with the T channel, say now this is a total energy, momentum transfer, then the same function can describe a different physical process happening in the T channel. Again, I will tell you the explicit example. Otherwise, it is too abstract. Same is true for this. So the crossing property states that the same amplitude can, in principle, describe 3 physically distinct processes, but it's basically the same analytic function or meromorphic function of ST. Okay? So let me first address this statistics question, and then let me give you an explicit example, how to see that happening. So to continue this, so let's in S channel, so suppose we are in S channel. Okay? So then suppose I have S channel, so without even specifying, suppose I have 2 identical particles, and then something comes out, right? So this will be an S channel. Okay? So suppose these 2 are identical particles. So just to make it absolutely clear, let me just put in N and N. So they are identical particles. So which means that amplitude, this thing, STU, so now I'm in the S channel, so let me just double score. They should be symmetric under P1 slot with P2. Right? So that's what Bosonic statistics will say. So then what it is? So T is a P1 plus P3 square. U is P1 plus P4 square. But by energy momentum conservation, this is equal to P2 plus P3 square. So these are related by swapping P1, P2. So what it means is that the S channel amplitude, so let me put S, so here S, has to satisfy PU is equal to S channel S UT. Okay? So amplitude will and has to satisfy this property. Okay? You can ask the same question. I'll just say T channel and then I move on. So in T channel, just to gain a picture, right? So then T channel I'm talking about now doing this. So 1, 3, 2, 4, right? So T channel, suppose I had there exist identical particles in initial state. Okay? So here really I'm talking about again N, that kind of situation. Okay? So that means P1 exchanged with a P3 should give me the same answer. Yeah? So what does that mean? So P1 plus P2 squared is S, and then P1 plus P4 is U, but then by energy momentum conservation, this is equal to what? 2 plus 3. You see now in T channel S and T, which are variables that captures the momentum transfer, right? They had to be now related by this bosonic statistics. So then the same statement in T channel is going to be there's S, T, U. Again, this plays a role of the total energy because that's why it's T channel. Has to satisfy U, DS. Okay? So this statistics picture can be captured or stated in what property, what symmetric property amplitude has to satisfy. Okay, so much of discussion for this abstract stuff. So let me take a concrete example to illustrate.
I have a quick question.
Yes.
Everything we're considering is like 4 legs. Is it possible if there are only 3 legs, like 2 things goes in and bang, there's only 1 comes out?
You mean decay, like 3 points?
Yeah.
In principle, you should be able to talk about that, but like there's no like ST to talk about, right? So it's just local vertex and then you're converting it to something. But you can ask whether loop level there's something meaningful to talk about. So decay, obviously you're sitting at the S channel, right? It sits at the rest frame of a massive particle, boom, and it decay into something. So in that sense, in a sense, heavy particle was sitting as in its S channel pole, and then converting into something. So it's possible, but I guess you get less about it, or you learn less trivial features about the amplitudes. Does that make sense? Yeah. Okay. Any other question? Good. Now let me actually introduce an example. Okay. So let's consider the following. So now I'm resolving this block. So what's inside of that block? Let me draw this diagram. Okay? And then let me draw also cross channel. Like that. Okay? So there's a phi, and well, I shouldn't specify n, but I'm biased already. I'm thinking of that way or that way. So that's what I'm putting. Oh, actually, let me not put that, because in some channels it's actually wrong to say that. So again, okay, so let me just put the momentum assignment. That's more consistent with the philosophy of talking about the crossing. So 1, 2, 3, 4. And then what is the momentum transfer? So in this case, well, it depends. But at least I can, because our convention is specified, this should be P1 plus P2, like so. This. So this is what? Who's going to help me? Oh, okay. So P2 plus P3, right? So if everybody in, and then coming out, everybody in, coming out should be this. Okay? Now, let's look at a S channel where here I'm taking this as my time element, for instance. Okay? So let me name it as this. So then this will be given by minus IG squared. So this first contribution, I'm reading this way, so I have to do this. So that gives me P1 plus P2 squared, and then minus M squared, like that. So let me not worry about the I epsilon prescription for now. And then the second one, the same thing, but gives me P2, P3 squared minus M squared. So that's the amplitude you're going to write. But let's actually write it as up to minus sign, P squared. So I'm going to write it as S minus M squared. And then this is 1 plus 4. So U. So this is the answer. So indeed, as promised, this thing will be a function of SPU in general. In this case, you will have an S and U. And you're not shocked because why? You already know that 2 to the scattering, you only need a 2 variable to describe. So indeed, you see only two variables appear here, right? Because of constraint we talked about here. Okay? And we talked about this, and that is like, cross momentum transfer channel. It gives you your Kawa potential if you go to the Fourier transform and so on. This will give you, this is S channel pole, so this will give you something like it's an IMT, sort of a free propagation picture. We talked about that, right? There's a time slice, you can cut it, and so on. You might say, oh, there's this pole. Why this thing doesn't give you pole? You can redraw this to avoid that confusion. I actually didn't want to erase it. That's right. That works. So again, just to complete yourself, you can draw slightly different way. So now if you draw this way, obviously there's no pole, right? There's no real pole. Okay, now, so that's S channel. Now let's do a P channel. Sorry, P channel. How do you go from S channel to T channel? Now you have to read the time from top to bottom. But when you do that, what was in stayed to be in, but what was out turning into the in state, right? Incoming state. In S channel, this was one of the outgoing particles. But when you read this way, now you have to turn what was outgoing into the incoming, right? So compared to S channel, I'm saying compared to S channel, P1 still stayed to be P1. What was in was still in. What was in now have to turn into the out, so you have to flip the sign as we talked about. What was out now have to turn it into the in state, so that should be minus P3, P4, stay to P4. What was out still out. Okay, so here, therefore, you're going to write it as, instead of just computing it, so here you can compute it if you like explicitly, but let me just use the crossing property. So then what happened is that the answer should be this. So I'm not changing P1, but P2 I have to change. And then both pick up the minus sign, so that minus sign goes away. Like this. And guess what? This is still this is still, if you want to write it in terms of SDU, this is still this. Again, it's the same, the point is the same function. However, you have to be careful. So this is still the same function as this. Okay? However, let me say a correct way of thinking about physics of this function now. Here, S plays a role of total energy, actually probing real pole. And then T and U will play the role of a momentum transfer. Okay? That's what's happening here. Here, in terms of a momentum assignment, so I'm not changing the labeling. In terms of a momentum assignment, this is correct expression. But if you were to compute the physics of this thing, pi go to, so this describes what? Pi n go to pi m. So that's the physics you're describing. But here, what you're actually describing is pi go to n and 1, right? That's what you're describing. So if you were to compute that thing, in fact, instead of calling P3, you would have called it P2, right? So what I'm trying to say here is that here, what plays the role of a total energy is actually P1 plus P3 squared, T. The fact that here you only see S and U, remember in T channel, S and U are momentum transfer. So this S is not a total energy, it's actually momentum transfer. So this physics only has a two different kind of momentum transfer structure. But modulo of that fact, it takes exactly the same meromorphic function as this one, even though they describe completely different physics, different process. Okay?
X채널 할 때 모든 모멘텀이 이제 안쪽으로 향한다고 저희가 했잖아요. 근데 T채널을 바꿀 때 이렇게 마이너스를 붙여주는 이유가 왜 그런 거죠?
Good. So because I put good. So suppose originally when I assigned P1, P2, when I wrote this answer, I wrote as if I assigned this way. Because if you remember, when we first write down the amplitude for this type of thing, obviously I assign the P1, P2 going in because I know which process I'm describing. And then I would assign the P3, P4 like that. Okay? So single amplitude, I would have done that. So, but if I follow our convention, if I assign everything like this, okay, then I would have this to be minus P3 sitting here instead.
그럼 지금 타임 방향에 대해서 좀 더 모멘텀이 같은 이렇게 흘러가고 있게 정리한 건가요?
Yes. When I wrote down this answer, I already assigned the momentum consistent with the time direction. That's why I had a plus P3 here.
그리고 오른쪽에 Q가 P2 마이너스 P3가 되는 거 아닐까요?
Oh, yeah, probably this is minus. There can be some minus sign error depending on how I did it, but the point is that yes, this could be P3 if I assign it that way. But then the point that I was trying to say here is that there's a relative minus sign between this and that. That was the point. So whatever you see P3, you have to see minus P3. Whatever you see P2 here, you should see minus P2. But there's no relative minus sign between P1 and P4. That's the important point. Is that clear? So you can choose whatever convention once and for all, and then there's a relative minus sign between these two processes, and that's the point. Okay? And then let me stress it again. These two are just literally the same function. And then if I use that to probe in the regime where S plays the role of total energy, this will give me amplitude associated with this process. And then this will get to interpretation in terms of total energy in the free propagation and the momentum transfer. Same function, on the other hand, if I go to, I raise the Mandelstam cable plot, go to the non-region where T plays the role of a total energy, then all of a sudden S and T will play the role of a momentum transfer. And then that gives me amplitude for this different process. Okay? Okay. Now, I'm gonna have to draw this again, but for a reason. So this is again, a cable, the Mandelson cable plot. These are physical region. So this is for S, this is T, this is U. Okay? Now, I draw this assuming that all the masses are identical, right? That's what I did. I did it assuming entire masses are identical. You might say, what if this is not true? How would this plot change? At least qualitatively. So, if you change this, what would happen is that close to threshold, things can in principle change. I don't know, some random way. Close to the threshold, this can change, like that. But the point is that if you go to the asymptotically large momentum, right? If you go to the asymptotically large momentum, then as you know, mass effect goes away. So it's as if everybody's massless, or as if everybody had the same mass. So asymptotically, you will just achieve, you go to the same shape, but you can change things a bit of a detail at near the threshold. Okay? But also crucially, it's impossible that these three physical regions overlap at all. Regardless of what you do, they will never overlap. So a function carefully described, same function carefully described in one part, this process, but never sensible that this same thing described another process simultaneously. They will not happen. Okay? So different reasons, this reason will not overlap. And so once and for all, this function will describe a unique one process if you go to the one point or the other. Okay? This is known as a crossing property. And also, this is importantly, this is a feature you see in the relativistic QFT. Because they are separated by 4m squared, 4m squared, 4m squared, they are separated by humongous energy scale. So you don't actually see like this process connected to that process by different analytic continuation. So this is basically analytic continuation. So take the same function, but I'm going to continue, take a value of complex variable into another region. So this is the process of analytic continuation. And the point is that same error function through the analytic continuation, it can describe the different physical processes. But the point is that they are separated by the large size of the energy, so it's hard to be seen manifestly in the non-relativistic region. So that's why people discover this problem when they study relativistic. Okay, so that's crossing. Now, let's briefly talk about the CPT. So now I'm actually talking about symmetry. So previously crossing is not a symmetry of a theory, okay? It is intrinsic property that amplitude can enjoy, but it's not about a symmetry. So now I'm actually talking about symmetry. So previously we talked about time reversal, parity, charge conjugation, right? We spent time thinking about it. So although a given QFT may not respect C or P or T or whatever CP separately. Okay? May not, and we have seen the examples. So that's the example is a standard model of particle physics. We often just write it as SM. Okay? Actually does not respect the CP, for instance. Okay? So it doesn't. Not only that, another example, you are called Varia. Your name is Varia. Congratulations. I'm Varia, you're Varia. And in fact, you're Fermion, I'm Fermion. and a gigantic composite nugget fermion. So in order to produce a baryon like you, universe or whatever underlying theory had to break, for instance, the CP. Okay? So in order to generate non-zero baryon, CP violation must be involved in the early universe. Okay? For technical reason. So from these types of example, you see that it's likely that in many cases in QFT you are dealing with the big break some of these symmetries separately, although that QFT, provided if it's a Lorentz invariant and two poles what is known as the spin statistics, meaning integer spin, it's a boson, half integer spin, it's a fermion. It's called spin statistics, okay? So integer spin, boson, they have to satisfy bosonic statistics, right? And then half integer spin, or fermion, they have to satisfy fermionic statistics. So provided that you have to satisfy this, has to respect CPT as a whole. It's called the CPT-theorem. Okay? And I never learned the proof of this. There's a famous book called, I forget, Spin Statistics, something like that. You may need some careful axiomatic quantum field theory to see that, or maybe there's just information. But anyway, instead of proving the CPT theorem or CPT-invariance, we're gonna just discuss what is the implication of that. If we accept this statement, what does that tell us in terms of amplitude? That's what we want to spend time on. It's brief. So, for a scalar QFT that we've been talking about, okay? In fact, given a P, so entire set of a P mu, we can implement a CPT transformation by performing this. So let's break up why this is true. So the quickest way to see it is this. So there's a P dot X, and then sending P to minus P can be reinterpreted in terms of sending X minus X. So this involves both sending T to minus little t, so that is known as a time reversal, and then X vector to minus X vector, that is a parity. So far, that's good. So P and T appears simultaneously. On top of this, you may recall that P to minus P in the context of a crossing, sending incoming particle to outgoing antiparticle. Right? Obviously, when I say incoming output, you already include the part of this feature, right? Sending T to minus T. Hello. There's a spy. Jesus. There's a spy. We are in danger. Okay. So now, by combining all these three facts, you see that in scalar field theory, thus sending P to minus P indeed performs a time reversal, parity, and charge conjugation. Okay, particle to antiparticle. So it does, as a whole, the CPT transformation. In fact, remember, the amplitude of scalar field theory is only a function of SPU. And S and T, U separately, if you send entire P, not just sending one of them, sending some of them correspond to performing crossing relation, right? Remember, let me be careful. Take this blob and then, if you flip one or two guy, you are going from one channel to the other. That's what you do in the crossing business. What I'm talking about in the context of CPT, I'm taking entire set of momentum and flip everybody to minus p. That's what I'm talking about. So then, obviously, they don't change, right? Remember, this is just basically a function of some pi plus pj squared. So if you flip the sign both simultaneously, nothing changes. So in fact, therefore, you see that this thing doesn't change. Okay? Now, what does this tell us about? What does this tell us about, for instance, fluid scattering amplitude? So let's talk about the S channel, right? S channel, I will have like P1, P2, minus P3, minus P4. Yeah? Okay? So, and then let's talk about T channel, P1 minus P2 plus P3 minus P4. Oh, do I have a space? I wished. Was that a 2 picture? Okay, I wished. I don't have a space, so tonight, hopefully this is in your heart, right? I can erase this away. And then EU channel, P1 minus P2 minus P3, and then plus P4. So recall, crossing said that single meromorphic function, you can describe all these different processes. That was the crossing. So here's my account. So crossing says that three processes can be described by the same amplitude, by a single amplitude. That's the okay. Now let's talk about a CPT. So take this, and if I do the CPT transformation, okay, what do you get? So then this is minus P1, minus P2, P3, P4. Yes? So if this describes 1 plus 2 go to 3 bar, 4 bar, now this describes what? 3 plus 4 goes to 1 bar, 2 bar. So time reversed correctly. Particle went into antiparticle. And if you think about it, theory also, because momentum is x over t. If you only need a time reversal, momentum changes the direction. But then if you want to have a also same momentum processing this thing too, also you have to do the parity, hence momentum doesn't change. Okay, if you think about that, so it's there. I mean, basically I'm repeating what I said here. Okay? So therefore, the statement of statement of a CPT says that this has to be the same as this, right? That's the CPT. It's actually a symmetry. Okay? But it's actually a different process, but amplitude is identical. What about this? So let's do the CPT. I get minus P1, P2, or P3, P4. So if this describes 1 plus 3 goes to 2 bar plus 4 bar, this thing describes, let's just look at the right positive side, 2 plus 4 goes to 1 bar, 3 bar. And then CPT-invariance says that this has to be the same. Lastly, let's just finish up for completeness sake. P1, P2, P3, minus P4. So this describes 1 plus 4 goes to 2 bar plus 3 bar. And this describes, I can read 2 plus 3 goes to 1 bar, 4 bar. And then again, CPT-invariance says that that's the same. So the full account is in this context of 2 to 2 scalar field theory. Crossing says a single function can describe 3 different processes related by the crossing. And then CPT says that there's a further additional another 3 processes which are this object. So total says that single function can describe the 6 processes. Okay, so that's basically we can talk about. Now, story can change, obviously, if we have spins and whatnot. But okay, anyway, this is what we can say about CPT. Any questions? Okay, now we will get real. This so far has been very nice conceptual aspect of amplitude. Now I will talk about actual rate, process rate. Okay. So now what I want to talk about is let me actually get the title of this. It says so now we will spend some time discussing. We've been so far talking about what? S operator. And then starting from S operator, we developed a diagrammatic method, right, for actual transition amplitude, right, from initial state to the final state. We developed the Feynman diagrammatic method and how to compute the amplitude, and we spent some time understanding some underlying structure that amplitude can have, right? How things are related and what are the CPT and so on. Now, here I will now derive what is the actual object you want to compute, as for instance, as an experimentalist. So if you smash two particles together and they produce a final state, what quantity do you need to compute as an observable? Okay, amplitude itself is not quite completely observable. Okay, you want to develop a notion of a probability in quantum theory. So here, key object we want to compute or derive is differential transition probability, which I will develop. If we can turn down the temperature. Do you agree that we want to turn down this a bit? It was hot, no? It was, you were wearing it. Strong man. All right, so let's talk about this. That's what I want to talk about. So until now, we've talked about basically S matrix. By S matrix, I mean we talked about there's S operator, there's an in state, there's an out state. Right? So we talked about this. And then how to extract amplitude out of that. That's what we talked about. Yes? So now I want to introduce the notion of a phase space. And then we will get this out, basically differential transition probability. And in fact we will focus on two different kinds. Although I will keep the discussion general, but eventually we want to talk about decay rate when heavy particles decay into several light particles. What is the decay rate? How to compute that? And then the second one I want to talk about is if I smash two particles together and then see what happens. There's a notion of cross section. Okay, but our discussion will be general, and then only at the end. I will basically consider these two specific cases. Okay, so to do this, let's do it. So to do this, let's put your QFT in a box. You'll see why this is useful. Okay, so let's put your QFT in a box. So let me do it. Let me do it. So here's my box. And let me keep whatever. The box size L. So if you do it, the first thing what happens to you is the following, right? So you will get, P dot L is 2 pi integer, right? That's what it happens. Okay, there's a wave function, if you like, there's a periodic boundary condition it has to satisfy as you go around, it should be the same as the original point, 2 pi n. So if I do x direction, y direction, and z, that direction you will have this, basically. So therefore px, py, pz will be now quantized. So let me scroll up. 2 pi over L, and x, and y, and z. So far so good. Okay? So far so good? Okay. Now, let's ask what happened to our quantum field. So what happened to the quantum field? So here is my continuum version of that, meaning L goes to infinity, so nothing in the box, but continuum version. I'm going to write everything once and for all carefully, because we want to have a careful translation of this. Although here, it's not very important that I talk about alpha beta separately, but so this is a continuum version. And if you recall, let me just remind you that the way we normalize this creation annihilation operator, same for the beta, was this 2 pi to, was that like p minus q. I'm not writing here, p, q is there, and then 2 p. So that was normalization of our creation annihilation operators, if you recall. Okay? This is a relativistically very normalization. So now I want to write this quantum field in this situation. Okay? So that's what I want to do. So to do this, let's note the following first. So the space-time volume, how would you write? Space-time volume is a d3x. I think that makes sense. Right? Okay. And 1. And so this is also can be written as up to plus minus sign I 0 x. And if there were p there, you would write it as p, which is a 0. Okay? So space-time volume, so if you look at this, obviously you just cry, oh, this is infinity, that's bad. How infinite that is as infinite as the size of the space and volume. Okay? You can do the same thing, v times t is d4x times 1, d4x into the minus 0, 0 vector dotted with the x, right? So space and time being both 0, and then this is 2 pi to the 4th, 0. So how infinite this delta 4 is, this is the same as scaling as size of the spatial volume, and then time, the total amount of time. So keeping this in mind, now let's go back to this task. So we already understood that delta function is v, the fourth version is v times t. So now we have to rethink about this thing. Okay? What I want to design is the following. So we want dimensionless creation operator. Okay? Such that if I have a physical state in a discretized, so this D is discretized, or discrete, meaning I put things in the box, that's what I mean. So therefore, the reason why I want this, as you will see, if I define my quantum state, momentum p in the discretized version, is action of this discretized operator acting on the vacuum. I want this to be dimensionless. Why do you want that? So let's compare. Before I motivate this, let's compare this versus what the way we have been doing in a relativistically invariant way is that I put this acting on the vacuum, and this carries a dimension. How much? Which is half of this dimension, right? Alpha delta carry this dimension. So our quantum state carries different dimension. This the half of that dimension. Make sense? Now, then why I want to talk about this dimensionless quantity? The reason why I want to talk about the dimensionless quantity is because eventually I want to define a notion of a probability. And the probability is a number, 0.5, right? And I want to have a probability which is valid even if I change number of a final state, for instance. Right? I want to talk about something that either decay into 2 particle, I want probability. 3 particle probability, right? And so on and so forth. But if a state itself carries dimension, as I change number of a final state, this thing will change the dimension all the way through, right? So I have to keep track of that. That's a big headache. So then the question is, can I, at least as an intermediate step of computation, can I define a dimensionless state? So 2 particle state, 3 particle state, n particle state is the same dimension. In particular, not only the same dimension, just dimension 0. It will be easier conceptually and then technically to just talk about the probability. Okay? So that's basically the motivation why we want to talk about it. But then here we go. So we can define that object. So here I want such that the normalization of this thing. So say I want to talk about the 1 particle state. Because I want it to be 1 rather than the delta function stuff. Okay. Okay, so now you know what to do. So basically, given alpha p, and as I said, this carries a dimension of a volume, right? That has a dimension of volume. So I want to define this to be a dimension of a volume half, because I'm talking about only alpha, half of it, 2e, and then dimensionless quantity. Okay, good. Now, we can write down this. So to do that, I have to talk about, how to think about this integral over dp3. Well, let's do it. So d p cube over 2 pi cube, and then I do the integral. So let's talk about this translation of that in the discretized version. By the quantization that we have written down, p over 2 pi to the cube is the same as 1 over L cubed, the summing over mode. Okay? So this gets translated into, what did I say? 1 over volume, sum over nx, n vector. Yes? So this is a triple sum, if you like. Okay? So I just literally use that. Good. So then I can rewrite my quantum field in the discretized manner as the first thing, I will have a 1 over v, and then I had a 2e. So let me just rewrite. So 1 over 2e, summing over both number. So I have written down this much. And then from alpha beta, I get this much. So v 2, and then I will have a Hermitian conjugate. So let me just say Hermitian conjugate, even though in principle, you can have a different operator creation of. Okay, so therefore discretized version of a field operator will be summing over mode number and then V, VP, and then that. Dimensionless creationizing operator and dimension conjugate. Good. So since we are here, now let me also translate this in terms of a discretized version. So now you just need to remember how this scales. That scaled like square root of V, square root of EP, and then I had basically this thing acting on vacuum. That's the definition of the discretized, which is a dimensionless. Okay, so basically I pulled out the relevant dimension, and then I kept the dimensionless part. Okay, and we will use this again and again and again. So maybe it's safe to write down somewhere. I mean, that's exactly this relation, right? State created by this guy, the state created by that guy is related by this vector. Okay. Any questions so far? Is it clear what I'm doing? I literally put in things in the box. I just doing the dimension analysis. Okay. So which one scales like volume? Yes.
디멘전레스 스테이트를 왜 도입해야 되는지 잘 이해가 안 되는데 아직.
Yes.
아까 이제 제가 넘버를 원하기 때문에 디멘전리스트 어떤 스테이트가 필요하다고 말씀하셨잖아요.
Yes.
근데 항상 어떤 앰플리튜드를 계산할 때 그 S 매트릭스에도 디멘전이 들어가기 때문에 결국에 앰플리튜드 자체는 디멘전리스가 된 거 아닌가요?
Yeah, good. So eventually you will see something dimensional. Okay? So both a decay and a cross section, eventually you will see something dimension 4. So decay rate will be dimension 1, cross section will be dimension -2. Okay? So if you want the better motivation is that I want to develop a machinery for computing differential transition probability, which is valid for arbitrary number of, if you like, final state, for instance. But if you state is self-carried dimension, different final state number will have a different dimension. So then you have to squeeze in, you have to struggle yourself to get the correct dimension. Okay? You will see basically now why that's useful. So by designing, by introducing a state that doesn't carry any dimension, allows us to talk about at once transition probability with arbitrary number of final state, for instance, also initial state too. But we will constrain mostly either one particle or two particle state in the initial state or final state. It's certainly, in other words, if you smash them together, the number of final state is out of your control. Right? Physics happens, it happens, and it can produce 2 or 3 or 4 or 5 million, it will happen. So in a sense, initial state, you are in a designer mode. You can say, I want to only smash 2 guys. Or I can just prepare a single guy and let it decay. You can design it. But final state, it's out of your control, right? It will just happen whatever. So we want to have a machinery or language that we can deal with a different number of final state at once. And for that, it's useful to have a dimensionless state, as you will see basically now.
Yes.
Okay, good. Any other questions so far? Okay, so let's move on. So in a sense, we are almost prepared to now talk about talk about a transition probability. Okay, so I want to define a transition probability. Although here, eventually we will have to be a little bit more careful. Probability is really number. There's something which is not completely dimensionless. I want to define this as like final state in the discrete sense, s minus 1, discrete sense, squared. So we've been dealing with this amplitude, I don't want to square that. But here I'm introducing, so this is manifestly dimensionless, right? So this is dimensionless, right? And if without a subtlety, which we will enter soon, without a subtlety, if this is dimensionless, and if this is also dimensionless, this is perfectly dimensionless. So it will be just a probability. Eventually, everything will be okay, except there's a one subtlety I need to address regarding this initial state, but it will come. So for now, we can just take this as a good notion of transition probability. Okay? In state, dynamics happens, turning into final state. So this is literally looking at the overlap of one state into the other, squaring it. That's what you do in the quantum mechanics. So here I want to talk about the final state and initial state separately. Okay? So for final state, so for instance, if you want to talk about like P1, P2, Pn, final state. Suppose you have an F number of final state particles. Then this will be equal to product of 1, 2, and F, square root of V, square root of E I, and then and F in the sense of relativistically invariant normalization, right? So here I just view that asymptotically, this is just a product state, and for each product state, I just literally apply this relation. Okay, and this is dimensionless. This definition is actually dimensionless. Like I said already, we have to treat in this physical processes that we will talk about. We have to treat the final state in a statistical manner. Okay, so exactly the same initial state can produce sometimes 2 particles, sometimes 3 particles, sometimes n particles, sometimes 10 particles. We don't know. So we have to treat all this as a probabilistic manner. Okay, genuinely. So once you collide something, what is the probability, for instance, to produce a 2 particle, right? Only a 3 particle. So everything is completely probabilistic in nature. Okay, and so everything, I'm just literally treating everything equally in this manner. That's just that. No, if you like, don't worry too much about it. All I'm saying here is that I literally apply this to each of the particles appearing in the final state. That's all I said so far. Okay, now, okay. Before that, maybe if I say what I'm saying, what I will say now, that will be helpful. So let me actually look into this relationship just a little bit more. Okay, and I think that will be illuminating. Let me erase this part. And if I say that, probably you may clarify what I mean by that here. Okay, so let's take that expression. I'm not talking about one particle state. So now I want to look at the probability of this guy. So if you do that, you get 1 over V, 1 over 2E from this, and then, not surprisingly, you will get this. And recall, if you do this, you will get 2 pi q delta 0 in the momentum space, and then 2E. So now let's just forget about the 2E factor for a second, okay? So what was the meaning of this? The meaning of that was this volume. So I can think of this as follows. I'm summing over volume from this vector, and then the probability to see a particle in this space-time volume at a point is 1 over V. So if I pick one point in space, and then I ask, what is the probability to see that particle? 1 over v. And then I'm summing over entire volume to say that therefore total probability is 1. So there's a damn one particle in this space somewhere. But each point, all I can say is that the probability is 1 over v, but since I'm summing over entire space, I get 1. That's how you can understand this expression. And now we see that putting this is giving away a probability for a particle to be seen or to be found at a given point in space is 1 over v equally everywhere. And so when I say that for final state, we're going to treat a probabilistically by putting all this factor to every particle you see in the final state, that's basically what I mean. So I'm just letting every particle as a probability to be seen 1 over v everywhere. Good. Now, let me talk about the initial state. That one has a bit of subtlety, only a small subtlety. And then we will combine things together to derive transition probability. Okay, so in a sense, for final state, no subtlety. You just do no-brainer. So for initial state, it's a different. Like I said, you prepare the initial state, right? For this particular experiment. So in this case, probability for a given initial state is 100%, right? You prepare, let it go. So here, let me divide into one particle state. So if the number of initial particle is 1, so number of initial particle is 1, then there's not much of subtlety. You again just pick what we have done. Because as I already illustrated, this thing has a correct probability, a correct picture. So you put that particle somewhere in space. And there's a 100% chance to get that guy if you actually look through entire space. Okay? So for one particle thing, think about the decay process. You put that particle somewhere and just wait. Detector covering entire space. Okay? And there's 100% chance that guy is sitting there somewhere in the space. You will decay, you just try to see what happens, right? So that's correct normalization. This gives you 100% probability that you actually prepared that particle, right? Somewhere in the space. Really subtlety happens when ni equals to 2. Other than that, everything is straightforward. So let me first say in word, and then write down the equation. So the first particle you put somewhere. So that's the same as this. So the first particle you prepare, you put somewhere, and according to this rule, right? So 100% chance that guy is there. But second particle, you don't put randomly somewhere, because then this will not lead to actual collision. So the second particle you have to put in the vicinity of the first particle. Okay? So you're not, for the second particle, you're not following completely flat distributional sense. You have to have a probability 1, the second particle to be seen in the vicinity of the first particle. Instead of saying the second particle is somewhere in the V. You see the difference? Okay, you prepare the first particle. If you naively put this factor even for the second particle, what you are saying is that I put second particle somewhere, I don't know where. Most of the time it will not be next to the first particle. So most of the time it will not lead to collision process. But as a particle physicist, we will prepare particles to collide each other. What that means is that I know that the second particle is prepared, with a probability, which is 1, to be seen right next to the first particle. Okay? So the question is, what is the correct expression to do that? So now I'm saying, okay, I'm summing over entire space. What is the probability to see the first particle? So that's that. Let me put 1 to indicate that this is the probability to be seen the first particle somewhere. And this is now a product of the probability, right? First particle, second particle. So if you have done just the second particle like this, which was the case that if you put this factor equally to both particles, this is what you get. And if you take the limit where this goes to V, obviously this probability goes to 0. Makes sense. If you throw two random particles, most likely they don't collide. So therefore, in order to overcome this problem, what do you have to do? So somehow you have to modify the probability distribution for the second particle, that it actually has a V enhanced probability to be seen. And this will give you probability equal to 1, right? So what it means is that for two particle states, so let me just write, so P1, P2 state, what you are doing, okay, so I want to resolve this notation because that just means what I mean. So let me just say two particle state in the discretized sense is that I want to put correctly this vector for the first particle. Okay, this is for the first particle. But then I want to enhance this thing compared to naive normalization for the second particle compared to P1, P2, this. Okay? So if you do that, everything is same except this V. So I'm basically doing P1, P2, discrete science, but I'm multiplying extra square root of V. And that's exactly this thing. So if you like, what I'm doing is throw the first particle, 1 over V chance to see somewhere. To make sure 100% the second particle bang on that guy, instead of throwing one particle in volume V, I have to throw out V number of the second particle into the V. But then I know the 100% chance that this will collide with the first particle. Does that make sense? So imagine you discretize the space in the 10 block. Okay? The particle can go into one of those 10 blocks. You first throw the first particle, it will be one of those 10 blocks. Right? If you throw the second particle randomly, only one guy, there's a probability to go into the one of the block 1 over 10. What if I throw like a 10 second particle? Then every time, the second particle go into one of those blocks, eventually at least there will be one guy, colliding with the first guy. So that's this basically multiplicity effect. Because that's how we produce unit state. We know there's 100% collision. Otherwise, you're not good experimentalists. You screwed up. Okay. So I think all the solo part was done. So now it will be streamlined derivation, transition probability. I think I only need 5 minutes or so to finish that. But and if you have any question, I would love to address. Okay, so I'm gonna now write down streamline derivation. So let me first define this. So I will write 2 pi to the fourth, there's I factor, delta 4, momentum conservation, and then I will define from initial to final and discretize. Sorry, let me just follow correct B times T to be basically final S minus 1. So far, nothing funny. And I'm saying that V is finite, T is finite. So I put the QFT in the box, gigantic space and time box. Okay? And then the usual amplitude, invariant amplitude, will be obtained if you send V to infinity, T to infinity of this regulated amplitude. Okay? So far I haven't done anything. Now I'm gonna use this fact. So final, every particle I will have this vector. Initial, so let me go. So that's the definition. So then the way we prepare initial state, discretized, is that because we are going to use either one particle initial state or two particle initial state, we are not going to consider beyond this. Okay? Because that's like you have to believe that like 3 particle, 4 particle all of a sudden collide each other. It's possible, but that's not what we are interested in. So we will only consider either one particle initial or 2 particle initial state. Then this can be written as for each initial state, initial particle state, we put 1 over 2e And then we will put only one overall factor of 1 over v. Okay, so this is outside of this problem. You might say I'm writing something fancy. No, I'm not writing something fancy. I'm just really writing this together. So for one particle initial state, we have 1 over 2e, 1 over v. For two particle state, I said instead of two factors, I'm just gonna multiply by that, so canceling that out. So for each particle, I still have 1 over 2e, square root of 2e, but I only have 1 over 1 factor of 1 over v. That's all I'm saying, okay? So there's only one factor of 1 over square root of v, for each particle, I will have this. And for final state, nothing funny, so we're gonna just have everybody equally this factor, initial NR, that's what I mean, and then final NR, okay? With relativistically invariant. Why NR? Why NR? Where did NR come from? Good. I don't think NR, this is non-relativistic, probably relativistically invariant. Probably I want to use RI. You know what I mean? Huh? You're happy? Okay, that's why you were not, you look not happy over it. So I'm very sorry for that. That's what I mean. Relativistically invariant. Or Lorentz invariant? Anyway, you know what I mean. My hand somehow remember this. I don't know. Something happened to me. Okay, so that's the preparation. Now, okay, I'm ready. That's right. So transition probability is this. Well, first let me write down this out. Okay, and then we are going to split. So how would you write? Well, let's write this. So I combine these two definitions. So I get the 4 momentum conservation in first. And then we will have times t, I put in the box. And then I need to write this in terms of relativistically invariant state, because that amplitude is defined in terms of relativistically invariant state, right? Okay, so, but then this one, starting out with the discretized version, I know how to relate that to the relativistically invariant state. This will therefore have times for each final state. We will have 2EF D, and then for initial, as we said, there's only this factor times overall stability. Okay? So far so good. Okay. So with that, now what is the transition probability? So therefore, now, transition probability is, the claim is, let me first write and explain. So let me explain this. So in order to get probability, first of all, I need to square this thing. Do you agree with that? And this is a probability with a fixed initial momentum configuration and fixed final momentum configuration. Okay? So this is a computing transition amplitude for specified initial, specified final momentum configuration, right? And then we compute this amplitude. But transition probability, to talk about it, you prepare initial, so that's still fixed. So this, I don't have a complaint about. But then, something happened to the final state, and then I have to ask, what is the correct density of state? You know, for instance, this thing produced with a certain momentum, what is the number of a state in that momentum direction? What is the, number of a state in another momentum direction? So this Therefore, you should factor in density of state, number of states in their particular momentum direction. So that we can understand because delta and f, number of a thing, is the same as by final momentum and by so basically here what I'm trying to say is that I'm using basically 2 pi n, right? I'm using this quantization property. So to talk about this, basically I need to talk about this, and then if I want to compute actual number of modes, Q, and then I have to Q, that's the volume. Okay? So for any given, now if I put differential in the sense that I'm gonna look at a infinitesimal momentum volume of the final state particle. That means that dn cubed is the same as times v. So that's what I'm doing. And I have to do it for every final state particle. So for a given number of final state particle, I should ask what is the probability, what is the number of state in that particular momentum direction. Okay? So here, therefore, I'm actually producting entire final state particle. That's what I'm doing. Good. So now I can write this. Let me do it. So let me first square this up. So don't worry about I. It's absolute square. So square means I have 2 factors of this. So one time I will have as it is total final momentum, total initial momentum. So that's lovely momentum conserving delta function. But then you have a square of that thing. So one delta function imposes the other delta function that the argument is 0. And I told you that what is that object? So that object is a v times t, if you remember. Okay, so that's the square of this factor. And then I have the square of that factor. T square, good. And this one, so for each product of a final state, I squared it. So it's 2EF, then V. Okay? But let me not stop there, because let me factor this in. So we will have, how should I write? Where, let me, oh no, actually let me just do it here, that's better. Pretend you never see this shit. It was there. And so let me, for each final state particle, I have to put this factor times V. So that's the density of state factor. And then for initial, I will have a 2EI for each initial, and then I have overall 1 over V. Good? I think I have done honest job. Now let's clean up. Let's clean up. So that V cancels. That's good. And then this V cancels. So good. So at least the one big infinity go away. Happy. We still have one infinity left out. So how do we solve the problem? Well, we just ask a different question. So differential transition probability per unit time. Okay, divided by dt is equal to, let me just write this first. Let me just write this first. 2EI for initial state. And then we have this, and then we have So for each initial state, you divide by 1/2e. Okay? So either 1 if it is a single particle decay, or 2 if it is a two particle cross section. And then dynamical information. So you know how to compute the Feynman amplitude, you have to square it. And then there's this gigantic object. We define this to be final state, relativistically invariant final state, density of state. So this, let me say, relativistic density of state. So that's the answer. Okay, good. So now this is pretty general, except the fact that the only thing that you need to remember is that this formula is valid to tackle either one initial particle or two initial particles. We could have done the other case, but okay, we don't need it. Physically, that's quite irrelevant. Okay, we don't smash three particles together. That's pretty hard to do. Okay, so I think the problem I should stop today. Next time, now I will just use this general formula to talk about the decay of particle. What is the special the Lorentz invariance or Lorentz non-invariance property of the decay? And then we will talk about the cross section of a smashing two particles together. Again, what is the Lorentz transformation property of the cross section? Okay, we'll talk about that. And then after that, we will slowly moving on to LSZ reduction. Okay, so that's all for today. Thank you for coming to the meeting.